One of the hardest things in the course is understanding surface area. Okay? You have to understand surface angles if you're gonna do fluxes. So you've got this surface out here, and you got this velocity field, you got some air blowing, okay? And air is blowing in different directions. In some places, there's some divergence, positive or negative. In some places, there might even be some curl. And you want to see how much air flows through this surface here because you're trying to design an airplane. Okay, and the surface probably doesn't look like this, could be anything, but it's some surface out here in 3 dimensions. It's not a plane region. Okay. So to do that surface integral, you need to isolate an area increment. Okay. And each area increment, if this thing has a wavy shape, it's going to be oriented in a somewhat different direction. So you have to have an area and a direction. Okay. The easiest way to do that is to parameterize your surface. We looked at how that can work last time. Okay. And I might just use that cone we talked about last time as a simple example, although that has a, yeah, I'll use it for afterward. Okay. Now what we did was we were able to parameterize that surface in terms of 2 parameters. Okay. T was one of them, theta I think was the other, was T and theta. Okay, remember that? Okay. You know, like in the XY plane, we have T sine theta, T or T cosine theta, T sine theta. X is T cosine theta, Y is T sine theta. Okay, and that gives you a circle of radius T in the XY plane. Now your Z coordinate was just, maybe it was just T. Or maybe it was 12T, or maybe it was 5, you know, some multiple of T. Okay, so that how far you go up is proportional to how far well to the radius of the circle. That's going to give you a cone. Now the point is that surface was parameterized by T and theta. Okay, and that's just 2-dimensional. Surface is 2-dimensional, even though it's in 3 dimensions. Okay. You can parameterize it with 2 parameters, it's 2-dimensional. You know, I'll go ahead and use it. I guess maybe I was going to do parabola, but I'll do that next. I'll just do our I don't know if Z was 4T before, let's just make Z equal 4T. It'll be a steeper cone than it would be if it was just T, right? Get the right words down there. If our cone can be defined in a 2-dimensional, theta T space. Doesn't matter which coordinates theta, which coordinates T. This is a flat. This is the plane. The plane doesn't look anything like the cone. But for every point here, there's a point X, Y, Z on that cone. Okay. And for any point, sample point here. Theta I star T J star. And any delta theta sub I or J delta T sub I, there's a region on that surface. So let's say any increment in sample point in the theta T plane corresponds to an increment in sample point on the cone. So it's like you got your cone here. So this increment in the sample point maps over someplace on the cone. And it might not be a perfect rectangle, but depends on the nature of your parameterization, but locally, it's going to be a rectangle, and we're going to calculate two vectors to define the area and the orientation of this. Well, it's got that, it might not be a rectangle, it'd be a parallelogram, but it's an approximate parallelogram. The sample point is obvious. We're in the T theta plane, but a theta I star T J star is going to give us an X and a Y and a Z too, isn't it? We just plug in T J star and theta I star, and we get an X coordinate, which would be this, except I think T has the J on it and theta has the I on it. Now it's going to be this. This and this. Now they're just as we get if we plug theta I star, TJ star into each of these parameterizations, okay? And each of these expressions within our parameterization. So now we know where this goes. I mean, if we know what Ti and theta J are, or TJ and theta are, okay? So if I give you two coordinates, and now we, of course, within this space, let's just say that this is defined for theta from 0 to 2 pi and t from 0 to 3. Well, that gives us a rectangle right here in the first quadrant of our t versus theta, our t theta t plane. Okay, theta goes out to 2 pi, t goes up to 3, and now you've got a rectangle. And do your interval over that rectangle. Okay. Now what we're doing is we imagine taking that rectangle, and chopping it up into increments, partition the t, partition the theta. That's an easy thing to partition because t and theta have constant limits. Okay. And what we're talking about is a sample point within that partition. That sample point corresponds to a point on cone. And the delta theta delta t interval here corresponds to an approximate parallelogram. From this, that parallelogram has a direction and it has an area. And we've got to figure out how to get the direction of the area. Very easy to compute, a little hard to get your head around exactly why it works and exactly what's going on. Okay, so we understand this much. Let's think about it for a second. Make sure you'll give me a minute to process it. And then we'll go on and try to figure out this part is fairly straightforward to understand. It's a little weird thinking of mapping from here to here. You've done mappings in linear algebra, you've seen how areas mess around. Okay, well, this is linear. This is definitely not linear. Stuff's linear down here, maybe. You know, we get out into three-dimensional space. It's not linear as heck, but it's still a transformation. You have a transformation from this space and this subspace of this or subset of the space to this cone. Okay. Such that if we have any coordinate here, we know where we are in the cone, we just plug the t and the theta coordinates in here, we get our x, y, z, and that's where we are in space. Okay, that's really what we've got. I don't want to worry about what happened to this area increment, but it's transformed over here, and that's a little harder. Let's make sure we understand this much then. Okay, people claim to be at least halfway to understanding what this is. That's all right to start with. Okay, some people think not too hard to understand. So what happens next? Well, here's where we might run into a little bit of a problem because I don't think people, the class as a whole, has done a great job of mastering the idea behind finding a vector perpendicular to a chunk of, a small part of a surface. Okay, you got a function f of x, y, and this surface is part of the graph or approximate part of the graph. Then the slope here is the y derivative, assuming y is in this direction. So it's f sub y, or partial of f with respect to y. So you get a vector, which would be j plus that partial derivative times k. The reasons for cutting these blocks up and risking my fingers and eyes and everything else. Just so you know, not that much of a risk. I'm not using tools, but and what would see this picture. Okay. I'm gonna come home right now. Okay. So, and of course, in the x direction, we've got a slope. So we have a vector I plus fxk. Now, f slope is negative, so fxk will be down instead of up. And we take the cross product of those, and we have a normal vector. Okay. And then if we take our delta x and multiply it by our delta y, Then multiply that by the secant of the angle. Here, we get the area of this thing. Okay. Okay. Well, hopefully, some of that is sunk in, hopefully all of it's sunk in. That's an important picture because you got to use it here. Okay, so what we do is kind of unfortunate I use T here because your book uses the vector T. Which is why I was going to switch to the parabola and I forgot that I was going to do that. Okay. So we got to make sure when we see this vector T, that this T is not the same as this T. This T is one of our parameters. I could go through and change all my T's to use if I wanted to. It's going to look a little weird. And it's, we don't have a T sub theta. It's just going to be partial F. So with respect to theta, well, let's demortize it. Okay. Okay, now theta in our parameter space, but this is the vector back out here in three-dimensional space where our cone lives. Okay. So here's our T theta. It's very easy to calculate it. And in this case, that's going to be this negative T sine theta I plus B cosine theta J. There's no K component. And what's that geometrically? You got your circle. And as theta increases, if T is positive, you go counterclockwise around the circle, right? And this is just a tangent vector, that circle. Okay. I mean, what's a tangent vector? Okay. You can see it geometrically. It's got negative reciprocal slope to the radial vector. And all that stuff that I hope you understand and know how to put together. You might have to think about that. Okay, but there it is. There are other ways like we can stick with that. Then you have T, unfortunately, sub T, where this T is the parameter, this T is the tangent vector. Okay. Okay, this is tangent to the curve, even when you're up on the cone. Okay, you got the circle down here. Well, it's just mirrored by a point, a circle that much higher on the cone because of the way Z. Okay. And you're still in a horizontal plane when you're on that circle, and this vector is in a horizontal plane. Okay. Parallel in a horizontal plane. Okay, so we do T sub T, which is this the analogous expression where your partials are with respect to T. What's this equal? Well, it equals cosine theta I plus sine theta J plus 4K. Right? Now notice that the cosine theta I and the sine theta j are perpendicular to the t sine theta I and the t cosine theta j. Okay. And that you also have a k component. Now, remember, we got our delta thetas down here. Not going to clutter this up with theta I stars and TJ stars, stuff like that. Okay. But I could put a delta theta sum I on this, and all my T's and thetas in the expressions I'm going to get could have the J stars and the I stars and all that stuff. And it would totally correspond to what we get when we map this thing over here. So what we're trying to do is we're trying to define this parallelogram. It's not a rectangle. Actually, I take it back in line, it's a rectangle. Because this is perpendicular to this. That's all there is to it. Okay, anyhow, our T theta, delta theta is going to be a vector out here in the space of the cone. Right? It's going to be tangent to the cone. Okay, well, T theta, delta theta is then so now the vector has a magnitude and a direction. And it represents approximately this side and this side of what we get when we map this thing onto the cone. So it's like, okay, you got this side here and this side here. So that this little increment of the cone, which I'll bring out here, might, depending on where this is, it might look like this. Okay. Where this vector is our P sub theta. I'm just debating whether we put an I star on it. I don't have room, so I won't. That's like our T sub theta delta theta. Okay, and so is this one. Then we have our T sub, unfortunately, T times delta T, too many T's in here. And that equals cosine theta I plus sine theta j plus 4k. Delta T. Right, well, let's use a contrasting color here and say, okay, well, we got our two vertical sides of this thing. It could be both represented by vectors, right? Move the hands of the arrows there. And they go here. And coincidentally, because of the nature of the surface, they are perpendicular, but they wouldn't always be. So we do get a rectangle here. So this would be put an arrow over my T here. Okay. This would be the vector T sub T delta T. All right. So we've calculated these two vectors that define the increment here that corresponds to this increment in our T versus theta plane. Okay. And as I said, it's easy to calculate. But you know, put this picture together and really understand what's going on, you're probably gonna have to think about it a little bit. Try to do the best I can to bring it out, this picture. Be nice to have a bigger picture there, but this might be. So my question then is, what is the area and what's a vector normal to this region out here in three-dimensional space on the cone? Okay, so I have again. This time, didn't want to say anything. I said, okay, two words. Well, immediately I heard cross product. And that's the key. That's the fundamental property of a cross product. You got two vectors. Not only should you know that their magnitude of the cross product is the area of the parallelogram. First of all, you got to know if they define a parallelogram. Second, you got to know that the area of the parallelogram is going to be the magnitude of the cross product. And the third thing you really need to know if you're going to understand the geometry of three-dimensional space in any way is why. Okay. Also, why does the triple product work? If you haven't worked that out, if you can't draw that picture in your head instantly, or at least on paper, if you're not good at visualizing, you need to know that. Okay, it's one of the most important things you know in this point. And a whole lot of important things. Okay, so area of the parallelogram, the area of the parallelogram and the normal of the parallelogram are both that's not a triple factorial, quadruple factorial of the cross product. That's just exclamation points for the to emphasize the importance of knowing and understanding this. The magnitude really bad looking to me down there. I don't think so. That's the area. And we say across the T is normal. Oh. That should be a vector. Perpendicular, say normal. Mobile your service in three dimensions. Okay. So. Give you a couple minutes, see what you can do. Might be a little bit of a stretcher. Would be surprised if hopefully you get it. So what's the integral for the area of this cone? Okay, what are we gonna do? Well, the area. Double integral. Of the area increment. Okay. Note I don't have an arrow over the top of this. I don't want to integrate the vector area. Okay, if I did, I would just end up with a downward vector. That might or might not have the same magnitude as the area. You need to think about that. Okay. So I'm going to say, well, just to emphasize this, it's going to be just the integral of the magnitude of this stuff. Okay. Now the magnitude of the dA is, I mean, here's your dA increment, right? It's magnitude of this times your d theta dt, right? So in at least one paper, I saw a d theta dt and a couple of integral signs out here, not sure what to put in. That's it. Okay. And then it's going to go. Zero that right. Okay. There it is. Okay. And you don't have to worry. You see a d theta and a dt, you're worried about, oh, is this r sine theta d theta or what, you know, what is it? Okay. That r sine theta thing or that rho squared sine phi sine cosine theta. That's in here. If it's appropriate, it's already taken care of. Because again, these vectors define the area. Okay, in terms of a delta t and which I've got a delta theta down here. Yeah, it's like it was over here. Too many T's. I'm not going to try to make excuses. There is none. Okay, so there we have it, right? Now you can then in the one integral I saw, you know, wrote all that up. Okay. This cross with this, I think I saw all the cross product. Pretty sure that's what I was looking at. So that's easy. It's an easy integral. It just involves sine thetas and cosine thetas and t's, powers of t maybe. T squared energy. And you have constant limits on your theta and t, which makes it real convenient. Okay, so this whole difficult question of how to do a surface integral comes down to something that's actually kind of simple. Okay. Now, we might want to do a flux integral. Okay. How do we do a flux integral? let's just let F be PI plus QJ plus RK work. We understand that F, P, Q, and R are all functions of X, Y, and Z, right? How do we do that? That's all in surface increment. F dot DA. Okay. If it might actually use the DS there for surface. So I wanted to use A just to emphasize area and not confuse the meaning. And the rotations. Yeah, using the S has its connotations also. This is a simple connotation. You might want to use a more sophisticated connotation. It's F dot DA because your picture is DA is normal to the surface. And here is your vector function you're trying to calculate the flux for. And you want the component of this thing that's in the direction through the increment. So you project this back onto here. Okay. And there's your F perpendicular. And then you multiply that by the area. But that just comes out F dot DA. And you really need to understand that picture and projections and all that stuff to be able to assemble ideas into understand what you're doing. Okay. So, and that's calculationally simple. If there's an F, well, we do the cross product here, but we don't put magnitude signs around it. And now we're doing the cross product or the dot product of F with this cross product. Time your delta thing, the delta two, is theta two. Okay. That's all. So once we have this area increment, this vector area increment, we do whatever we want to do. Okay. At least as far as things like flux and so on. Circulation would be circulation. Surface as well. Okay. So that's all I'm going to say about it. If you have that picture, then everything that the book tells you and everything, every example tells you is just an application of the picture. I was going to do a paraboloid, but I think maybe we need a little more comment on some of the stuff in the other side. Okay. For example, Green's theorem. Attempted to do an example of the Green's theorem where your integral around the boundary is easier than the integral over the region. Okay, or vice versa. The integral over the region is easy, but the integral, the line integral over the boundary is incomprehensible. Okay, I like to do those examples, but I guess as far as this week, this is the big thing I wanted to focus on, because I think it's a hard stuff. Okay, well, let me find an example because I don't want to make one up. Okay, it'll just take me a minute to find. I'll just pick one randomly out of open math because I've got some examples.